You know, for nearly a century, there's been this one problem in computer science that's been like a giant, unbreachable wall. It's called the halting problem, and for as long as it's existed, it's been famously, fundamentally unsolvable. But what if that's not the whole story? What if that wall isn't actually real and we've just been asking the wrong question this whole time?
Okay, let's get right into it. Our story kicks off way back in 1936 with this incredible paper from the one and only Alan Turing. Now, he wasn't just thinking up a new kind of machine, he was trying to define the very soul of computation itself, drawing a line in the sand to map out the absolute limits of what any machine could ever possibly do.
And buried inside that foundational work, he described a problem that has pretty much haunted computer scientists ever since. It's a question so tricky, so wrapped up in its own logic, that he actually proved it was impossible to answer, and that is the halting problem. For decades, that was it. End of story. The problem was unsolvable. But lately, a completely new way of looking at it has popped up, and it asks this really fascinating question. What if Turing's proof wasn't about an impossible problem at all, but about a question that was just badly phrased? What if a smarter question could actually get us a real answer? To really see how that's possible, we first have to get our heads around why everyone thought this thing was unsolvable to begin with. So let's break down Turing's original and, honestly, brilliant argument. So at the very heart of all of this is the Turing machine. Now, don't let the name scare you. Just picture a simple little robot with a super long strip of paper tape. All it can do is read a symbol on the tape, write a new one, and move left or right, all based on a really simple set of rules. Believe it or not, every single computer you've ever used is just a really fancy version of this basic idea. And for Turing, this wasn't just some abstract concept. He saw this machine as a direct mirror of how a human mind works through a calculation. The tape is our scratch paper, the rules are the methods we learn in school. He was basically trying to model the process of thinking itself. Okay, so this leads us to the ultimate question. Imagine you had the world's best spell checker, but for code. A single master program, let's call it a decider, that could look at any piece of software you give it and tell you with absolute certainty, is this program going to finish its job and stop or halt, or is it going to get stuck in an infinite loop and just run forever? Now, this is where Turing's genius really kicks in. He showed that this master program, this halts function, could never exist. And he did it by creating this tiny, mischievous little program that basically uses the halts program against itself. We'll call our little paradox maker UND. All it does is ask the halts program to analyze it, and then it does the exact opposite of whatever halts predicts. Let's just walk through this because it's a real mind-bender. So option 1, the halts program looks at UND and says, true, this program will definitely halt. Well, UND is programmed to see that true and immediately enter an infinite loop. So the prediction was wrong. Okay, what about option 2? What if halts predicts false? This program is going to loop forever. Well, then UND is built to see that false and just halt right away. The prediction is wrong again. No matter what answer the decider gives, it makes itself a liar. It's a perfect, rock-solid paradox. And that, right there, is why the halting problem was called unsolvable. Okay, so for decades, that was that. Game over. But what if it's not? A researcher named Nicholas Swenson has proposed that the problem isn't the paradox itself, but the job we gave the decider. What if we could build a decider that was smart enough to see that paradox coming? And this really gets to the heart of the whole shift in thinking. See, the original decider asks a really simple question: does this program halt? But the new, smarter decider asks a two-part question: does this program halt? And this is the crucial part, will my answer end up causing a paradox? The secret sauce that makes this possible is a concept called call context. It means the decider isn't just looking at the program's code in a vacuum. It's also looking at the situation it's in. It's asking, how is my answer actually going to be used by the program that's asking? That context is the key to seeing the trap before it springs. As Swenson himself puts it, the new decider has a prime directive: do no harm, or more accurately, do not create a contradiction. It will only give the answer true if that answer is actually going to stay true once the other program hears it. Logical consistency is rule number 1. So let's go back to our little troublemaker program, UND. The new context-aware halts function looks at the situation and it sees that if it says true, UND is designed to go into an infinite loop, making that true answer a lie. So to avoid that contradiction, it has only one logical choice. It has to return false. Now our unprogram gets that false result, and just as it's programmed, it halts. Now here's the really subtle part. The prediction wasn't technically right about the final outcome, but the system as a whole avoided a logical collapse, which was its main goal. All right, so that little thought experiment works. But Turing's original proof was, well, a lot more complex. It used a powerful method called diagonalizing. So the real test is, can this new context-aware decider handle the main event? Okay, so Turing imagined a machine, we'll call it H, that could list every possible computer program in existence. It then creates a brand new program by taking a piece from each program on the list, the first bit from the first program, the second bit from the second, and so on, and changing it. This creates a new, unique diagonal sequence. But, you guessed it, the paradox pops up when H gets to its own name on the list and has to analyze itself. And, just like with our simpler example, the context-aware decider has an escape hatch. It sees that if it declares H satisfactory, which basically means it will halt, then H is programmed to immediately go into an infinite loop. To keep everything logically sound in that specific context, it must declare H unsatisfactory. Paradox averted. So this is where it gets really clever, even a little weird. When machine H gets to its own spot in the line, it knows it can't analyze itself without causing that paradox. So it just sidesteps the problem. It skips itself. And for its own position, it just copies the output from the next machine in the list, machine I. And as you can see, the final diagonal sequence is still complete, it's still totally valid. The trap is avoided without wrecking the whole system. And here's what makes this whole idea so solid. This new decider isn't some magic wand that makes all paradoxes vanish. If you try to build a machine that computes the opposite of the diagonal, it still breaks. And why? Because it's a true, fundamental paradox for a program to logically produce an output that is, by definition, the inverse of itself. That is genuinely impossible, and this new system correctly flags it as impossible. So, what does this all mean? If this holds up, by just asking the question a different way, we've found a path around what was supposed to be an absolute unbreakable limit. What could that mean for the future of computers? Well, honestly, the implications are pretty staggering. If the halting problem is solvable, that might be the key to solving a whole family of other so-called undecidable problems. It could lead to a future where we can automatically prove our software is safe and will never get stuck in a deadly infinite loop. It would fundamentally redraw the map of what we thought was possible. I think the big takeaway here is almost a philosophical one. Maybe these hard limits we've accepted for so long aren't actual walls built into the universe. Maybe they're just reflections of the questions we've been asking. And a better question could open up a whole new world of possibilities. And that's the thought I really want to leave you with. If the most famous unsolvable problem in the history of computer science can potentially be cracked just by reframing the question, what else is out there? What other impossible things are just sitting there, waiting for us to finally ask the right question?